Welcome to the Yawning Theories, where we gently unwind with the fascinating chemistry of nearly everything. From the quiet dance of atoms to the barely audible chaos of colliding molecules, tonight's journey explores the invisible forces shaping our world. I'll do my best to keep things soothing, but fair warning, the universe is incredibly captivating. If you enjoy this calm, curious content, please consider liking and subscribing. It helps this cozy corner of the internet thrive. And if you'd like to share, let me know where you're listening from and your local time. I love seeing how far sleepy science travels. Settle in. Let your breath slow and let the day's thoughts drift away. Tonight, we'll discover why things react, bond, explode, or sometimes do nothing at all. A quick note. While we'll touch on body and brain chemistry later, this isn't medical advice. Just friendly, fact-checked bedtime science. Imagine an object in your hand. A spoon, a feather, a cookie. Now imagine cutting it in half repeatedly until you can cut it no more. You'd reach something so fundamentally tiny it stops being that object and becomes an atom. Atoms are the building blocks of all matter. Everything around you, your pillow, your toenails, your tea mug, this screen, is made of them. You are a walking, talking, occasionally yawning cloud of organized particles. And while atoms are incredibly small, the science behind them is anything but boring. Let's start at the very beginning. An atom has three main particles: protons, neutrons, and electrons. If atoms were solar systems, protons and neutrons would be the central sun, forming the nucleus. Electrons would be the speedy planets, zipping around in what we call orbital. However, electrons behave more like clouds of possibility than precise dots. They exist in fuzzy regions where they're likely to be found. Elusive like introverts at a crowded party, the nucleus is dense and central. Protons have a positive charge, while neutrons have no charge. Together, they form the atom's heavy heart. Protons define an element. 1 proton means hydrogen, 6 means carbon. Add or subtract a proton, and you change the element entirely, like a strict name-tag policy at a cosmic conference. Neutrons, though neutral, are crucial peacemakers. Without them, positively charged protons would repel each other with immense force. Neutrons act as diplomatic glue, bringing calm to a tense subatomic space. Now, the electrons, these are the sprightly, nimble ones. They carry a negative charge and occupy various energy levels or shells around the nucleus, gaining energy as they move farther out. Electrons are the social butterflies or lightning bugs of the atom world, constantly darting, shifting, and leaping to higher energy states when energized by heat or light. Here's where it gets even more intriguing. Atoms are mostly empty space. If a nucleus were the size of a pea, the nearest electron would be hundreds of feet away. This means everything solid you touch, including your own body, is made of particles suspended in vast voids of nothingness. Matter feels solid not due to density, but because of the invisible forces between these particles. Like standing in a room with invisible walls, each atom is incredibly small, about 1/10,000,000th of a meter in diameter. A single grain of sand contains more atoms than there are stars in the observable universe. Yet each atom follows the same quiet choreography of attraction, repulsion, bonding, and occasional rebellion. When atoms combine, they form molecules which then form everything else: gases, liquids, solids, stars, and you. Even a single atom tells a fascinating story. Take helium: 2 protons, 2 neutrons, 2 electrons. It's light, unreactive, and aloof, preferring to float solo. Then there's oxygen, a social type always looking to pair up, essential for every breath you take. You could imagine atoms at a party, helium quietly sipping punch in the corner, while oxygen and hydrogen dance, forming water and making a splash. Of course, not all atoms are stable. Some are radioactive, their ambitious nuclei decaying over time, releasing energy. It's a dramatic end for something so tiny, yet it powers everything from smoke detectors to the Earth's core. Even instability has its role in this vast atomic drama. What's remarkable is how predictable all of this is. Centuries of science and experimentation, allow us to understand atomic behavior with impressive accuracy. We can map configurations, predict interactions, and even manipulate atoms to build new materials, medicines, and technologies. It's the ultimate blueprint, requiring no instructions, just a deep understanding of the rules and immense patience. Atoms also form the periodic table, that beautifully ordered grid of elements you might recall from school. Each square represents a different atom with a unique personality. Some gregarious, others stubborn and solitary. Some heavy and slow, others light and reactive. The table is a character map for the universe's fundamental players. Despite our vast understanding, atoms remain full of wonder. They obey the strange rules of quantum mechanics, where particles can exist in multiple states, and observation can alter behavior. It's science at its most poetic and perplexing. Atoms don't think or feel, and they certainly don't know we're discussing them. But if they did, perhaps they'd be amused that these tiny, invisible bits of existence are the stars of the show. Quietly, invisibly, they shape everything, including our thoughts, dreams, and breath. So here we are, nestled in a world built from countless tiny somethings, mostly empty space, dancing according to laws followed for billions of years. And yet from all that stillness and emptiness, life emerges, consciousness emerges, and you emerge. It all starts with the atom, the smallest something that makes up everything. Let's take a moment to appreciate electrons. The tiny, zippy, wildly unpredictable particles responsible for nearly every chemical reaction you've ever witnessed, smelled, or accidentally created in a school lab. Electrons may be lightweights, almost 2,000 times less massive than protons, but what they lack in size, they more than compensate for in energy and attitude. Electrons don't behave as we'd expect. The deeper you delve into their world, the stranger it becomes. If protons and neutrons are the dependable folks holding down the fort in the nucleus, electrons are more like excitable artists on roller skates, constantly moving, difficult to pin down, and prone to dramatic action given the right conditions. Let's begin with the basics. Electrons carry a negative electric charge and are drawn toward the positively charged protons in the nucleus, much like a moth to a glowing light bulb. This attraction prevents them from drifting into the void, but it doesn't mean they settle down quietly. Electrons are in constant motion, and their behavior isn't described by a neat orbit like planets around the Sun, but by something far more elusive. The probability cloud. In classical physics, you can describe an object's precise location and trajectory. But electrons don't follow classical rules. They belong to the quantum realm, where location and momentum are slippery concepts. Instead of a dotted line, scientists use a fuzzy cloud of probabilities to show where an electron is likely to be found at any given moment. The denser the cloud, the more probable the electron is in that spot. Like searching for a cat in a large house. You don't know its exact location, but based on past experience, it's likely curled up near a warm window under the bed or inside a cardboard box. These clouds or orbitals come in various shapes and sizes, spherical, dumbbell-shaped, or something a sleep-deprived artist might dream of. Orbitals are grouped into layers called shells. Electrons are fundamental to atomic structure and reactivity. Each electron shell surrounding an atom's nucleus can hold a specific number of electrons, with the innermost holding 2, the next 8, and so on. Electrons prioritize filling lower energy levels before moving to higher ones, a principle known as the orb principle. They only occupy higher shells if lower ones are full or if they absorb additional energy. An atom's reactivity is primarily determined by its outermost electrons, called valence electrons. These reside in the highest energy shell and are most likely to interact with other atoms. A full outer shell signifies stability and unreactivity, much like a content individual. However, an incomplete outer shell prompts the atom to gain, lose, or share electrons, initiating chemical bonding. Consider noble gases like helium and neon, which have full outer shells and exhibit minimal reactivity akin to contented introverts. Conversely, elements like sodium, with a single valence electron, readily seek to shed it for stability. Chlorine, needing just one electron to complete its outer shell, eagerly accepts it. The interaction between sodium and chlorine, where sodium donates an electron to chlorine, forms sodium chloride table salt. This pursuit of stability, often described by the octet rule, explains why atoms form specific bonds. Atoms engage in various electron manipulations, sharing, stealing, or donating, to achieve a full outer shell. In covalent bonds, electrons are shared equally, a peaceful exchange. In ionic bonds, one atom completely transfers an electron to another, forming oppositely charged ions that are strongly attracted. Energy plays a crucial role in electron behavior. Absorbing energy from heat, light, or electricity can excite electrons, causing them to jump to higher energy shells. They quickly return to lower energy levels, releasing the absorbed energy as light, a phenomenon behind neon signs, cosmic gas clouds, and fireworks. Electrons also account for metals' shininess and conductivity. In metals, electrons are delocalized, forming a communal cloud that moves freely throughout the structure. These mobile electrons reflect light, giving metals their luster, and facilitate the smooth flow of electric current. In chemistry, electrons are the ultimate arbiters, influencing whether atoms bond, the type and strength of the bond, and its ease of breakage. Reactions begin when electrons are displaced from their usual positions by external stimuli. Beyond chemical reactions, electrons shape the physical and chemical properties of matter, affecting appearance, feel, and behavior. They determine states of matter, acidity, conductivity, and even the colors we perceive. Pigments absorb and reflect light wavelengths based on how their electrons respond to energy. Despite their ubiquity, electrons remain a mystery, governed by the counterintuitive rules of quantum mechanics. They exhibit wave-particle duality, can exist in multiple locations simultaneously until observed, and can even tunnel through seemingly impenetrable barriers. Though tiny, electrons are the restless hearts of atoms, constantly in motion and influencing the world around them. From molecular bonds to electrical currents and even human thought, electrons are the invisible forces shaping reality. Without them, the universe would be dull and dark. If atoms had personalities, chemical bonds would be their relationship statuses, all driven by a fundamental quest for stability. Atoms seek lower energy states, and bonding facilitates this, representing a deeply logical pursuit of balance rather than sentiment. Covalent bonds exemplify mutual equal sharing, like two children sharing a snack fairly. Two atoms contribute an electron each to be shared, a peaceful arrangement common among non-metals. For example, oxygen and hydrogen share electrons to form water, completing their outer shells and giving water its unique properties. Conversely, ionic bonds represent a more aggressive interaction where one atom outright takes an electron from another. This transfer creates charged ions that are then drawn together by electrostatic attraction. Sodium and chlorine illustrate this, with sodium donating its electron to chlorine, forming sodium chloride crystals. Metallic bonding is a different social dynamic, akin to a communal potluck where no one claims ownership of a dish. In metals, outer electrons are delocalized, wandering freely through the entire structure. This electron sea enables metals to conduct electricity, reflect light, and be shaped without breaking. The driving force behind bond formation is energy. Atoms seek the lowest possible energy state, and bonding releases energy, moving them from a higher energy solo existence to a more stable bonded state. Valence electrons are the matchmakers in this process, as atoms with incomplete outer shells are highly reactive, seeking partners to complete their shells. Bond strength varies greatly. Diamonds, for instance, are incredibly hard due to the rigid network of strong covalent bonds between carbon atoms. Hydrogen bonds, while not full chemical bonds, are weaker attractions between water molecules. that give water its high boiling point and surface tension. Bond strength is influenced by atom types, electronegativity, an atom's ability to attract electrons in a bond, and how tightly electrons are held. Fluorine, for example, is highly electronegative, while cesium is more relaxed about electron custody. When bonds form, energy is typically released exothermic reaction, and when they break, energy is absorbed endothermic reaction. This explains why starting a fire requires energy input to break bonds. But once new bonds form, energy is released as heat and light. Chemical reactions often involve a complex interplay of bond breaking and forming, which can be slow like rust or rapid and explosive like fireworks. The world is a tapestry woven by countless invisible bonds, each striving for atomic stability. Our own bodies are a symphony of ongoing chemical reactions, driven by these fundamental electron interactions. Chemical bonds are fundamental to existence, extending beyond mere structure to underpin function, life, memory, and change. From proteins folding into precise shapes via covalent and hydrogen bonds, to DNA strands held by base pair attractions, and enzymes forming transient relationships with molecules to accelerate vital reactions, bonding is pervasive. Even our thoughts rely on neural firing, dependent on ionic exchanges across cell membranes. Ultimately, bonding is chemistry's means of creating order from chaos. Whether atoms share evenly, steal outright, or contribute to a communal pool, the objective remains constant: lower energy, greater stability, and the potential to build something new. This explains transformations like gas becoming liquid, or liquid becoming solid, all due to the ceaseless ways atoms link, rearrange, and hold one another. It's truly poetic that the same forces binding salt crystals are at work in stars, cells, and snowflakes. Everything we perceive owes its existence to these tiny atomic partnerships, a silent, perpetual dance of give and take. Energy is the driving force behind every chemical reaction, an invisible currency exchanged as atoms form or break bonds, reshape, or transform. However, most reactive chemicals require an initial push, known as activation energy, the minimum energy needed to start a reaction. Without it, even promising ingredient combinations would remain inert. Consider a box of matches. It contains all components for fire, but nothing happens until friction provides the activation energy. This heat increases molecular vibration, causing bonds to stretch, break, and new ones to form, leading to combustion. Without that initial spark, the match remains unlit because molecules prefer their current arrangements unless jostled. Activation energy is that crucial nudge. To visualize activation energy, imagine pushing a boulder over a hill. The boulder represents reactant molecules at the base. The uphill effort is the activation energy. Once the boulder crests the hill, it effortlessly rolls down the other side, similar to how reactions, once past the energy barrier, proceed easily. Some reactions require minimal energy, while others need a significant amount. This explains why some chemicals remain stable for years, while others ignite with the slightest provocation. It's not just about what molecules can do, but the energy required to compel them. After a reaction begins, energy is either absorbed or released, leading to two types of reactions: endothermic and exothermic. Endothermic reactions absorb energy from their surroundings, like photosynthesis, where plants convert carbon dioxide and water into glucose and oxygen using sunlight. Instant cold packs, which absorb heat from surroundings to lower temperature, are another example. Conversely, exothermic reactions release energy usually as heat or light. Combustion is a dramatic instance where candle wax reacts with oxygen to produce heat and flame. Fireworks, explosions, and even food metabolism in your body are driven by exothermic reactions. Your cells are essentially controlled combustion chambers, breaking down sugars in manageable, enzyme-regulated exothermic reactions to power bodily functions. Some reactions are reversible, shifting between endothermic and exothermic states depending on environmental conditions. like water evaporating endothermic and then condensing exothermic. Interestingly, many seemingly explosive reactions involve relatively modest changes in chemical bonds. The drama comes from the speed and quantity of these changes. A pile of leaves slowly decomposing over months is a chemical reaction, but the same leaves set ablaze transform in seconds. Both processes rearrange carbon, hydrogen, and oxygen atoms, but at vastly different speeds. Catalysts can influence activation energy by lowering the energy barrier, making it easier for reactants to reach the tipping point. They facilitate molecular interactions without being consumed. Enzymes, biological catalysts, are vital for nearly every process in living organisms. Without them, bodily chemistry would be too sluggish for survival. Catalysts don't provide energy, they merely smooth the path. The concept of activation energy also clarifies why some substances are unstable. If a molecule is in a high-energy state, a small nudge can cause it to collapse into something else, as seen with explosives or reactive chemicals. They've already met most of their activation energy entry fee and await an opening, which can be heat, light, friction, or even time. Safety measures often revolve around controlling this energy threshold, which is why volatile chemicals are stored in cool, dark places, medicines are refrigerated, and aerosol cans worn against heat. All molecular energy management. Chemical reactions are nature's way of reorganizing atoms to achieve a more comfortable energy level, akin to adjusting pillows for comfort. Some atoms prefer warmer arrangements, others need a warm-up, and sometimes a spark is essential. Whether it's the warmth of a hand warmer, the coolness of a cold pack, or a candle's soft glow, we observe energy in motion, transforming and sometimes exploding. It's never random. There's always a reason, usually the precise amount of energy arriving at the opportune moment. We often take these transformations for granted. Flicking a lighter, stirring ingredients, or watching sunlight, without realizing the energetic ballet at the atomic level. Behind every flame, breeze, and breath lies a reaction, sparked, balanced, and driven by the rules of energy, often initiated by a small push. Acids and bases are the mood makers of the chemical world, enlivening reactions. They can cause metal to fizz, change solution colors, or even turn cabbage juice into a chemistry experiment. Though often seen as opposites, they are two sides of the same reactive coin, defined by their interaction with water and their handling of hydrogen ions, H+, and hydroxide ions, O. Water itself is in a constant, delicate balance, with a tiny number of molecules constantly splitting into H+ and O ions and then recombining. An acid increases the concentration of H+ ions in water, acting as a generous donor. A base, conversely, either removes H+ ions or adds ions. Essentially, acids shift the balance towards more H+, while bases tilt it towards more O. The pH scale, ranging from 0 to 14, measures the balance between acidity and alkalinity. A pH of 7 is neutral, like pure water. Below 7 indicates acidity, with lower numbers signifying stronger acids e.g. G to B acidities, such nuts. Way walls lemon juice at pH 2, vinegar at pH 3. Above 7 indicates basic or alkaline solutions, with higher numbers meaning stronger bases, e.g. baking soda at pH 9, bleach at pH 12-13. This is a logarithmic scale, meaning each whole number represents a tenfold difference in acidity or basicity. Or basicity meaningsy. At extreme ends, both acids and bases can be corrosive and reactive. Acids are reactive due to their tendency to release hydrogen ions H+. These ions can alter chemical structures, speed up reactions, or damage tissues, explaining why strong acids can burn. Bases, conversely, either absorb these hydrogen ions or release hydroxide ions O to neutralize them. This dynamic interaction between acids and bases, a tug-of-war over H+ ions, is fundamental to countless chemical reactions. Acids and bases are ubiquitous. In the human body, hydrochloric acid in the stomach aids digestion, while the pancreas releases bicarbonate to neutralize it, maintaining a delicate balance. In cooking, acids add flavor and can tenderize meat or curdle milk into cheese. Bases, though less common, are vital. Baking soda, for instance, releases carbon dioxide when mixed with an acid, causing dough to rise. A fascinating aspect of acid-base chemistry is neutralization, where an acid and a base combine in the right proportions to form water and a salt. This reaction can be subtle or dramatic. The reaction between vinegar acid and baking soda base is a classic example, producing carbon dioxide gas, water, and harmless salt. However, mixing strong acids and bases like vinegar and bleach can be dangerous, potentially releasing toxic gases. The influence of acids and bases extends beyond visible reactions. They can modify molecular structures and influence chemical pathways, acting as catalysts or inhibitors. In living organisms, pH sensitivity is critical. Enzymes, vital for bodily reactions, are highly pH dependent. Extreme pH can denature them, leading to serious health issues. The human body maintains a tight blood pH control around 7.4. Some organisms, like acidophils and alkaliphiles, have adapted to survive in extreme pH environments. Environmentally, pH plays a significant role. Acid rain and ocean acidification, caused by pollutants and increased carbon dioxide, respectively, harm ecosystems by altering the pH of water bodies and soil. Industrially, acid-base chemistry is crucial in processes like wastewater treatment, battery technology, e.g., sulfuric acid in car batteries, dye-fixing in textiles, and cleaning products. Indicators are valuable tools in acid-base chemistry. These substances change color based on pH, such as litmus paper turning red in acid and blue in base, or phenolphthalein going from colorless to pink in basic solutions. Even red cabbage juice can serve as a natural pH indicator, showcasing a spectrum of colors. These transformations highlight the visually engaging nature of acid-base reactions. At its core, acid-base chemistry is about balance, a dynamic interplay of giving and taking ions. From neutralizing a wasp sting to aiding digestion, it involves ions interacting, electrons shifting, and molecules rearranging. Acids and bases, seemingly opposites, are partners in a molecular negotiation, seeking a stable, neutral state where chemical processes can settle. Beyond acid-base chemistry, temperature and pressure are also master manipulators in the chemical world, influencing molecular movement and reactions. The kinetic molecular theory explains this. All matter consists of particles in constant motion. Increasing temperature adds kinetic energy, causing particles to move faster, collide more frequently, and with greater force. This increased collision frequency and energy make reactions more likely, as seen in baking cookies or food spoilage. For a reaction to occur, molecules need to collide with sufficient energy and in the correct orientation. Pressure significantly impacts reactions, especially in gases. Increasing pressure forces molecules closer together, leading to more frequent collisions and a higher probability of reaction. This is akin to a crowded space, increasing the likelihood of people bumping into each other. Temperature and pressure not only affect reaction speed, but also influence the types of reactions that occur and the favored products. Some reactions require extreme conditions, while others reverse with altered conditions. This is vital in industrial chemistry for optimizing yield and efficiency, as exemplified by the Haber process, which produces ammonia under high temperature and pressure. Temperature also impacts the reaction rate constant, as described by the Arrhenius equation, demonstrating how even small temperature changes can drastically alter reaction speed. Temperature greatly influences reaction rates by increasing the proportion of molecules with sufficient energy to overcome the activation energy barrier. Essentially, heat helps more molecules reach their tipping point. Beyond speed, temperature also alters the nature of substances, causing phase changes like melting solids into liquids or evaporating liquids into gases. These are physical changes, as the molecules remain the same, but they demonstrate heat's power to disrupt structure. While most reactions speed up with heat, a minority may slow down if high temperatures destabilize products or shift equilibrium. This is why sensitive biological systems have an optimal temperature range. Too cold and processes slow, too hot and things unravel. Pressure, primarily affecting gases, can also impact reaction rates in solids and liquids, especially when system volume changes during a reaction. Increasing pressure can drive a reaction forward if it produces fewer gas molecules, or slow it down if it produces more. This is about shifting the balance to favor less crowding. The interplay of heat and pressure is evident in daily life. Pressure cookers, for instance, trap steam and raise internal pressure, increasing water's boiling point, leading to faster cooking without drying out food. Deep-sea chemistry showcases extreme pressures hundreds of times higher than at sea level, altering gas behavior, solubility, and reaction pathways. Microorganisms near hydrothermal vents thrive in these conditions, using heat and pressure for unique biochemical reactions, demonstrating life's adaptability to thermodynamic constraints. In the lab, chemists precisely manipulate temperature and pressure. Reactions taking days at room temperature can finish in minutes when heated. Pressurized vessels, autoclaves, enable reactions not possible in open air. In pharmaceutical manufacturing, temperature control ensures the correct structure and purity of delicate molecules. However, managing these factors is a delicate art. Too much heat can decompose sensitive compounds, and excessive pressure poses engineering challenges for containment. Sometimes the goal is control, allowing slow, predictable reactions to minimize unwanted byproducts or explosions. These principles are universal. Whether baking bread, studying volcanoes, designing rocket fuel, or fermenting yogurt, the same basic rules apply. Heat adds motion, pressure adds proximity, and together they subtly and spectacularly influence chemistry. Even weather is governed by these rules. Clouds form as warm, moist air cools and condenses. Lightning is charge separation in turbulent, heated clouds, and thunder is the sound of rapidly heated, expanding air. Much of what we observe is shaped by invisible forces acting on tiny particles. Molecules don't decide to react. They are guided by energy, movement, and proximity. Heat provides speed, pressure provides the squeeze, and together they unlock transformation, one collision at a time. From ice to steam, from crushing ocean depths to a humming kettle, particles dance, move, collide, and respond to their environment. At its heart, nothing reacts without motivation, and temperature and pressure are excellent motivators. In textbooks, chemical reactions often appear as one-way streets, with reactants forming products and the reaction completing. However, in reality, chemistry is rarely so final. Reactions are often reversible. Molecules combine, separate, and endlessly flip back and forth. This is the realm of reversible reactions, where the finish line is a roundabout, not a dead end. A reversible reaction is a chemical process that can proceed in both directions. Reactants become products, and products can break down into reactants. It's a chemical tug-of-war where neither side fully wins, and the system settles into a state of balance called equilibrium. Equilibrium doesn't mean inactivity. Molecules are still forming and breaking apart at equal rates. It's like people walking up and down an escalator at the same speed. The number of people at the top and bottom remains constant, but movement never ceases. The concept of chemical equilibrium is central to understanding natural and industrial processes. It explains why some reactions never seem to finish, why others appear to stall, and why environmental changes can tip the balance. Chemistry inherently seeks balance between competing forces. Consider a simple, reversible reaction. Colorless hydrogen and iodine gases react to form deep purple hydrogen iodide. Initially, purple gas forms. As hydrogen iodide accumulates, some breaks back down into hydrogen and iodine. Eventually, the rate of hydrogen and iodine combining equals the rate of hydrogen iodide splitting apart, resulting in a dynamic mixture of all three gases when nothing appears to change, yet everything is constantly moving. This equilibrium is delicate, depending on temperature, pressure, concentration, and catalysts. Henri Le Chatelier's principle, from the 19th century French chemist, provides helpful chemical wisdom. A system at equilibrium will counteract any disturbance. Imagine a room with a thermostat. If a window opens and cold air enters, the heating system activates to restore the set temperature. Chemistry behaves similarly. Adding more reactants shifts the reaction to consume them, producing more products. Removing products causes the system to replace them. Increasing heat makes the system absorb that heat, often favoring the endothermic direction. For example, the equilibrium between brown nitrogen dioxide and colorless dinitrogen tetroxide. At equilibrium, the mixture has a faint brown tint. Cooling the gas fades the brown as more dinitrogen tetroxide forms, absorbing heat. Warming it deepens the brown as more nitrogen dioxide appears. The system constantly adjusts to undo the introduced change. Pressure works similarly, especially for gases. Increasing pressure by squeezing the gas shifts the system towards the side with fewer gas molecules, attempting to reduce pressure. If the reaction produces more gas molecules, rising pressure shifts equilibrium to counter it. It's about molecules spreading out or huddling based on crowding. Even the concentration of individual substances can sway equilibrium. Adding a chemical tilts the reaction to consume it, while removing some causes the reaction to replace it. This is chemistry's graceful, reactive, and persistent adjustment to change. Equilibrium is crucial in biological systems. Our bodies rely on countless finely tuned reversible reactions. Hemoglobin, the oxygen-carrying protein, binds oxygen in the lungs, high oxygen concentration, and releases it in tissues lower oxygen levels, an elegant automatic adjustment with every breath. The carbonic acid equilibrium in our blood is another vital example. Carbon dioxide dissolves in water to form carbonic acid, which breaks down into bicarbonate and hydrogen ions. This reversible reaction maintains blood pH within a narrow range. If carbon dioxide levels rise, more acid forms, lowering pH. If they fall, the reaction reverses. This system with the lungs and kidneys maintains chemical harmony in the body. In industrial chemistry, mastering equilibrium determines success or failure. The Haber process, synthesizing ammonia from nitrogen and hydrogen, is a reversible reaction. Manipulating temperature, pressure, and concentration allows chemists to shift equilibrium to favor ammonia formation, a constant balancing act between chemistry and efficiency. Equilibrium doesn't mean equal amounts of reactants and products. It means forward and reverse reactions occur at the same rate. The mixture might be mostly products or mostly reactants, depending on the reaction's energy dynamics, which direction is more stable, and the energy required for interconversion. There's a poetic quality to equilibrium. It suggests nature prefers moderation, compromise, and feedback loops over extremes. The world isn't full of reactions that go one way and stop. Instead, it's full of reversibility, of systems that adjust, respond, and settle into a surface calm with underlying motion. This constant push and pull means nothing is ever truly finished reacting. Even in a bottle of vinegar, tiny shifts occur. In the atmosphere, gases constantly exchange, react, and redistribute. Even in solid rocks over long periods, atoms rearrange, minerals transform, and equilibrium slowly drifts. Equilibrium is a dynamic pause, a point where change balances itself out. It's when a tug-of-war rope stops moving, not because pulling ceased, but because both sides pull equally hard. It's peace through motion, not stillness. Understanding this principle offers a deeper view of the world. Balance is everywhere. In chemical reactions, ecosystems, and social dynamics, systems respond to pressure, resist disruption, and find new steady states. Chemistry effectively demonstrates how this works. The next time you encounter something in balance, see steam condense, or simply take a deep breath, remember, equilibrium isn't the end of a reaction. Explosions, often perceived as dramatic and terrifying, are fundamentally rapid energy releases stemming from chemical reactions. They represent chemistry operating at high speed, typically in confined spaces, and are characterized by a sudden expansion of matter and the release of heat, light, gas, and shock waves. While chemical reactions are a common cause, physical processes like decompression or nuclear events can also lead to explosions. The defining characteristic is the immense energy release occurring within milliseconds. Most chemical explosions involve combustion, a reaction where a substance quickly combines with oxygen to produce heat and light. While combustion can be gentle, like a candle flame, altering conditions such as increasing fuel or oxygen, or tight containment, can transform it into an explosive event. A hydrogen-filled balloon, for instance, becomes explosive with a spark, as hydrogen rapidly reacts with oxygen to form water vapor, causing instant air expansion and a shock wave. The core of most explosions is rapid oxidation, where fuel molecules lose electrons to oxygen, releasing energy as bonds break, and new, more stable ones form. This energy release, gradual in a slow burn, is unleashed all at once in an explosion, akin to a suddenly released, tightly wound spring. Controlled explosions can be harnessed for beauty, as seen in fireworks. Each firework is a miniature chemistry lab containing oxidizers, fuels, and color-producing compounds. Upon ignition, the oxidizer facilitates rapid fuel combustion, generating hot gases that propel the firework skyward. The bursting effect and vivid colors are created by different metal salts, e.g., strontium for red, copper for blue. TNT, trinitrotelluride, is a famous explosive where fuel and oxidizer are within the same molecule. Detonation causes rapid atomic rearrangement, producing gases like nitrogen and carbon monoxide, and a massive heat release. Its stability under normal conditions means it requires a detonator, a more sensitive explosive, to overcome its activation barrier and initiate the rapid self-propagating reaction. Explosions are categorized as deflagrations or detonations based on reaction speed. Deflagrations, like gunpowder, involve subsonic reaction spread, while detonations involve supersonic reaction fronts and create damaging shock waves, differentiating a firecracker from a high-powered explosive. Accidental explosions can occur when ingredients combine under incorrect conditions. The kitchen, surprisingly, is a common site for these. Flour, though seemingly harmless, can cause a dust explosion when suspended in air and exposed to a spark due to the large surface area of its tiny particles. This explains why flour mills have explosion-proof equipment. Aerosol cans containing flammable propellants can burst explosively if heated. Overheated oil catching fire, followed by adding water, leads to dangerous fireballs as water rapidly turns to steam, ejecting burning oil. Even the seemingly innocuous baking soda and vinegar reaction, while not dangerous, demonstrates rapid gas expansion. Explosive reactions are also practically applied. Car airbags utilize a controlled explosion of chemicals like sodium alzide, which rapidly decompose to nitrogen gas, inflating the airbag in under 1/10 of a second, potentially saving lives. In mining and construction, explosives like dynamite and ammonium nitrate and fuel oil are used to move large quantities of rock and earth, designed for stability during handling but capable of immense energy release upon proper detonation. Explosions also occur naturally. Volcanoes exemplify Earth's dramatic chemistry, combining heat, pressure, and reactive gases. Deep underground, molten rock, water, and gases build pressure until eruption, releasing heat, ash, and gas explosively. Even on a microscopic level, cells can experience miniature chemical explosions. The bombardier beetle, for instance, defends itself by mixing hydrogen peroxide and hydroquinone, which, catalyzed by enzymes, trigger a violent, heat and pressure-releasing reaction, propelling a scalding spray. Explosions are not inherently negative. They are simply fast reactions involving bond breaking, formation and energy release. The challenge lies in managing them. Too slow, and the reaction fizzles; too fast, and it destroys. Chemists, engineers, and even cooks skillfully manage this balance, harnessing explosive chemistry for diverse applications, from powering engines and launching spacecraft to saving lives and entertaining crowds. Explosions, rather than being outliers, are accelerated reactions governed by the same principles of energy, molecules, and the rate of change, whether in a candle flame or rocket fuel. Therefore, observing fireworks or popcorn exploding in a microwave showcases the same fundamental process. Atoms rapidly rearranging, accompanied by heat, sound, and expansion, chemistry unleashed, not chaotic, but fast and sometimes magnificently loud. Carbon, the diva of the periodic table, stands out for its versatility, charisma, and range. Despite not being the flashiest, heaviest, or rarest, carbon's ability to bond up to 4 times simultaneously makes it exceptional. This magic number allows carbon to form incredibly stable, flexible, and complex structures, including chains, rings, branches, double and triple bonds, forming the foundation of all known life. At the heart of organic chemistry, the study of carbon-based compounds is carbon's unique ability to self-bond catenation with itself and other elements in endless combinations, a talent unrivaled by any other element. Organic molecules are essentially carbon frameworks adorned with functional groups, small atomic clusters that dictate a molecule's behavior. These groups, like costumes in a play, assign specific roles, e.g., O for alcohol, Q for carboxylic acid, NH2 for amine, allowing carbon to play almost any part. Carbon also excels at building intricate structures. Simple straight chains can branch, bend, or form rings, such as cyclohexane's 6-carbon hexagonal structure. Aromatic rings like benzene exhibit further sophistication with resonance structures, where electrons form a shared cloud, imparting unusual stability and chemical interest. Organic molecules range from massive proteins, long amino acid chains folded into precise shapes, and DNA, a double helix of billions of atoms, to tiny methane molecules, 1 carbon bonded to 4 hydrogens. Regardless of size, the principle remains. Carbon acts as a central hub, forming bonds in all directions, holding everything together like a master networker. Carbon's 4 bonding arms also facilitate double and triple bonds. Double bonds involve 2 shared electron pairs, creating stronger, shorter bonds than single ones. Triple bonds with 3 shared pairs are even stronger and shorter. These bond types alter molecular reactivity and geometry, adding depth and complexity to organic chemistry. Isomers highlight carbon's versatility. These molecules share the same chemical formula but possess different structures. Carbon can arrange the same atoms into distinct shapes, leading to compounds with vastly different properties. Butane and isobutane, for example, both C4H10, have differing structures that impact their boiling points, melting points, and chemical reactivity. Stereochemistry adds another layer, where molecules with identical atoms and bonds can be mirror images like left and right hands. Enantiomers, with their identical chemical formulas but distinct 3-dimensional arrangements, exhibit dramatically different biological effects. One version of a drug might alleviate pain, while its mirror image could be inert or even detrimental. Living organisms interact with molecules with incredible specificity, a precision enabled by carbon's unique ability to arrange itself in 3-dimensional space, contributing to life's exquisite tuning. Organic chemistry, sometimes playfully called the chemistry of life and carbon-based confusion, lives up to its name with a multitude of molecules, lengthy names, and numerous exceptions to its rules. Yet, within this complexity lies a beautiful order, a system built on a small atom with grand ambitions. Life as we know it is essentially a prolonged carbon experiment. The four major classes of biological macromolecules, proteins, lipids, carbohydrates, and nucleic acids, are all carbon-based. Enzymes which catalyze bodily reactions are intricately folded proteins, each designed for a specific task. Cell membranes are constructed from lipid molecules, forming flexible, self-sealing barriers. Carbohydrates like glucose provide immediate energy, while starches and cellulose offer structural support and storage. DNA, the helical blueprint of life, carries genetic code within a molecule composed almost entirely of carbon, hydrogen, oxygen, nitrogen, and phosphorus. All these vital functions, energy storage, instruction replication, and structural building, hinge on carbon's capacity to form stable yet dynamic bonds. It's strong enough to maintain molecular integrity, but flexible enough to allow for change, movement, and mutation. A crucial balance for life. The very origin of life likely depended on carbon chemistry. Scientists exploring early Earth conditions, or simulating environments on other planets, often investigate how simple carbon compounds might have spontaneously formed, establishing the foundation for more complex structures. Laboratory experiments, using gas mixtures and electrical sparks, have successfully produced amino acids and other building blocks of life. These findings suggest that with the right components and sufficient time, carbon possesses the remarkable ability to create something extraordinary. Organic chemistry's influence extends far beyond biology, impacting material science. Carbon is the basis for everything from synthetic polymers to advanced nanomaterials. Plastics, whether for good or ill, are organic compounds, long chains of repeating carbon units. Carbon nanotubes and graphene are pushing the boundaries of strength and conductivity, promising innovations from flexible electronics to space elevators. Even fuels such as gasoline and natural gas are hydrocarbons, carbon chains with hydrogen sidekicks, rich with stored energy awaiting release. Carbon's versatility is also evident in its pure forms. As graphite, it is soft and slippery, ideal for pencils and lubricants. As diamond, it is hard and brilliant, a lattice of carbon atoms interconnected in an exceptionally strong three-dimensional network. The fundamental difference between these two substances lies not in their atomic composition, but in the arrangement of those atoms, the same element, yet entirely different properties. Furthermore, carbon is a central player in climate chemistry. Carbon dioxide, a simple molecule comprising one carbon and two oxygen atoms, is an essential greenhouse gas. While vital in small concentrations, its excess poses a significant problem. Its heat-trapping ability has made it a focal point in discussions concerning global warming, sustainability, and humanity's collective environmental impact. Carbon is not merely the substance of life, it is the substance of consequence. Despite its profound significance, carbon is not visually striking. It's typically black or colorless and only sparkles when compressed into its diamond form. However, in the atomic realm, carbon is the quiet genius. It constructs the molecules of life, the materials of modernity, and the cycles of nature. It bends, bonds, loops, and links in ways that other elements can only aspire to. If chemistry were a theatrical production, carbon would assume multiple roles: writer, director, lead actor, and set designer. Always present, always involved, yet rarely drawing attention to itself unless outcomes are spectacularly successful or catastrophic. It's the reason our bodies are composed of molecules instead of moon rocks, the reason our cells function, our food digests, and our brains think. Every heartbeat, breath, and blink of an eye can be traced back to this single element, possessing four bonding arms, an affinity for structure, and an infinite capacity for connection. Carbon is not merely the star of the periodic table, It is life's storyteller. Redox, a term that might conjure images of futuristic cleaning products or sci-fi robots, is in reality one of the universe's most crucial chemical processes. Short for reduction, oxidation. Redox reactions fundamentally involve the exchange of electrons, the tiny energetic particles that govern atomic behavior. Whether something is burning, rusting, charging, or digesting, redox chemistry is silently at work. At its core, a redox reaction resembles a synchronized game of electron musical chairs. One substance relinquishes electrons and another acquires them. These two processes, oxidation and reduction, are inextricably linked. One cannot occur without the other, as electrons do not simply vanish. If one atom releases an electron, another must accept it. A continuous chemical relay of give and take. Defining these terms, oxidation is the loss of electrons, while reduction is the gain of electrons. This might seem counterintuitive, as reduction typically implies a loss, but in chemistry, gaining negatively charged electrons makes a species' overall charge more negative, or reduced. A useful mnemonic to remember this is oil rig. Oxidation is loss, reduction is gain. Electrons are the energetic currency of atoms, constantly exchanged during a redox reaction. Some atoms are natural electron hoarders. Oxygen, for instance, is highly effective at attracting electrons, explaining its prominence in oxidation reactions. Others are more generous, readily shedding electrons to achieve a more stable configuration. Consider a simple yet classic redox reaction, the rusting of iron. When iron is exposed to water and oxygen, it gradually transforms into iron oxide, the reddish-brown, flaky substance found on old garden tools and forgotten bicycles. Here's the breakdown. Iron atoms lose electrons, becoming oxidized. These liberated electrons are then absorbed by oxygen in the presence of water, thereby reducing the oxygen atoms. The product is iron oxide or rust, which is chemically stable but structurally weak. Left unchecked, rust will progressively degrade the iron, necessitating constant protection for metal bridges, ships, and cars. Rust isn't merely a surface stain, it signifies an electron transfer that fundamentally alters the underlying material. While rust represents a slow, pervasive example of redox in action, other redox reactions are more energetic. Combustion, for instance, is a rapid oxidation reaction. When wood, gasoline, or a marshmallow burns, the carbon and hydrogen in the fuel lose electrons to oxygen, releasing energy in the form of heat and light. This swift electron transfer triggers a cascade of bond breaking and formation, producing flames and warmth, a chaotic yet beautiful manifestation of redox chemistry. However, redox isn't solely about disintegration, it's also how your body generates energy. Within your cells, a process called cellular respiration breaks down glucose, an energy-rich sugar molecule. During this process, electrons are stripped from glucose and channeled through a series of proteins in the mitochondria, creating a controlled flow of electrons that ultimately drives the production of ATP, the cell's energy currency. Oxygen acts as the final electron acceptor in this chain, explaining our need to breathe. Without oxygen to capture these electrons, the entire system would cease. This meticulously organized electron flow mirrors the mechanism of a battery. Batteries are essentially portable redox reactions. A typical battery contains two distinct materials, an anode which readily donates electrons and a cathode which eagerly accepts them. When connected in a circuit, electrons flow from the anode to the cathode via the wire, powering devices like flashlights, phones, or musical birthday cards. Inside the battery, ions move through an electrolyte to balance the charge, completing the circuit. In a simple alkaline battery, the anode is typically zinc, which undergoes oxidation, losing electrons. The cathode is manganese dioxide, which is reduced as it gains those electrons. The entire setup is designed to facilitate this electron flow in a controlled, steady manner, generating electricity without flames or sparks, a silent, reliable demonstration of redox. Rechargeable batteries, such as lithium-ion ones, utilize reversible redox reactions. When charged, electrons are pushed backward through the system, restoring the original chemical states, like rewinding a movie to watch it again. These reactions require careful balancing, a key aspect of brilliant yet challenging battery design. Redox reactions are also fundamental to photosynthesis, the process by which plants convert sunlight into sugar. In a green leaf, light energy splits water molecules, detaching electrons from hydrogen and channeling them through an electron transport chain. These electrons ultimately aid in converting carbon dioxide into glucose, storing energy in chemical bonds. This is the inverse of cellular respiration. Instead of burning sugar for energy, the plant uses energy to synthesize sugar. In both scenarios, electrons are in constant motion, exchanging hands in meticulously coordinated sequences. In laboratory settings, redox reactions are employed in processes like electroplating, where a metal object is coated with a thin layer of another metal. An electric current passed through a solution causes metal ions to gain electrons and deposit onto the object, either protecting the surface from corrosion or simply enhancing its shine. Your silverware, jewelry, and chrome car parts may all owe their finish to redox reactions. Redox chemistry even plays a role in health monitoring. Blood glucose meters use tiny redox reactions to detect sugar levels. Breathalyzers detect alcohol through oxidation. Many water treatment systems utilize redox reactions to eliminate harmful contaminants, either by oxidizing them into less dangerous forms or by reducing them into filterable substances. One of the most intriguing aspects of redox is its connection to electron affinity, an atom's desire to gain electrons and ionization energy, the effort required to remove an electron. These properties dictate which participants win and lose in the chemical game of musical chairs. Fluorine, for example, is the ultimate electron hog, the unsung heroes. Catalysts and enzymes catalysts are fundamental to countless processes, both natural and industrial, enabling transformations without being consumed themselves. In biology, enzymes, life's catalyst catalase, protects cells from oxidative stress by breaking down hydrogen peroxide into water and oxygen. Amylase in saliva initiates starch breakdown into simpler sugars, which is why bread can taste sweet when held in the mouth. Environmental sensitivity. Enzymes are highly sensitive to temperature, pH, and salt concentration. Extreme conditions can cause them to denature, lose shape, and function, highlighting the importance of homeostasis for biological processes. Beyond biology, industrial catalysis, Haber-Bosch process. Ion catalysts are crucial for synthesizing ammonia from nitrogen and hydrogen, a process vital for producing fertilizers that feed billions globally. It's estimated that half the nitrogen in our bodies comes from this catalyst-dependent process. Versatile applications. Catalysts are essential in manufacturing plastics, pharmaceuticals, and synthetic fuels. Zeolites, microporous minerals, refine petroleum by precisely sorting hydrocarbons. Transition metals like palladium and rhodium enhance efficiency in fine chemical synthesis, leading to significant cost saving. Green chemistry. Catalysts promote sustainability by reducing energy consumption, minimizing waste, and enabling reactions under milder conditions, making chemistry more environmentally friendly. Biomimetic catalysts. Inspired by natural enzymes, these synthetic compounds offer similar specificity and efficiency, a rapidly growing field bridging biology, chemistry, and engineering for advancements in medicine and materials science. Switchable catalysts. Some catalysts are designed to activate or deactivate under specific triggers, useful in drug delivery, activating only under certain conditions, or smart materials, changing properties with heat, light, or acidity. The essence of catalysis. Catalysts are the quiet force that make the impossible routine. They facilitate change, accelerate progress, and are the smooth operators of chemistry. making complex reactions feasible and efficient. They embody the idea that significant influence can come from subtle, behind-the-scenes actions. Water, the extraordinary everyday molecule water, H2O, is deceptively simple yet profoundly peculiar, bending the rules of chemistry and acting as the bedrock of life. Water's unique properties. Polarity. Water is a polar molecule with slightly positive hydrogen ends and a slightly negative oxygen end due to oxygen's higher electronegativity. This creates a molecular tug-of-war, making it behave like a tiny magnet. Hydrogen bonding. This polarity allows water molecules to form strong attractions, hydrogen bonds, with each other. These bonds, though not true chemical bonds, are powerful enough to high boiling point. Unlike similarly sized molecules, e.g. methane, water is liquid at room temperature. Surface tension, cohesion, and capillary action. These properties allow insects to walk on water, plants to draw water upwards and contribute to its unique behavior. High heat capacity. Water absorbs and releases large amounts of energy with minimal temperature change, acting as Earth's thermal cushion and moderating coastal climates. Expansion on freezing. Most substances shrink when they solidify, but water expands. Its hydrogen bonds form an open hexagonal structure in ice, making ice less dense than liquid water, which is why it floats. This is crucial for aquatic life survival in winter. Universal solvent. Its polar nature makes water an excellent solvent for ionic and polar substances, enabling nutrient transport in organisms, mineral absorption by plants, and effective cleaning. Like dissolves like explains why non-polar substances like oil don't mix with water. Role in biology. Water is the medium for countless biochemical reactions within cells, influencing protein folding and thus function, stabilizing structures, and participating directly in reaction. In photosynthesis, plants split water to extract electrons for sugar production, releasing the oxygen we breathe. Planetary impact. Water sculpts landscapes, drives weather systems through evaporation, condensation, precipitation, and moves heat globally via ocean currents. The continuous water cycle links oceans, clouds, rivers, and living organisms. Chemical reactivity. Water can act as both an acid and a base, crucial for pH balance and buffering in living systems. Scarcity of fresh water. Despite its abundance, less than 1% of Earth's water is readily available fresh water, with most locked in oceans, glaciers, or underground. Search for life. The presence of liquid water in space, e.g. Europa, Enceladus, Mars, is a key indicator in the search for extraterrestrial life, as it is a necessary ingredient for life as we know it. Human composition. Adult humans are about 60% water, with it cushioning joints, regulating temperature, and transporting nutrients and waste. The wonder of water. Water is a rule bender and shapeshifter, a vital and fascinating molecule that quietly enables life. Mixtures. The art of coexistence in chemistry. Not all chemical interactions involve dramatic transformations. Many are about substances simply coexisting, blending, or separating without forming new compounds. This realm of mixtures, solutions, and suspensions is fundamental to everyday chemistry. What defines a mixture? No chemical reaction. Unlike chemical reactions where atoms rearrange to form new substances, components in a mixture retain their original identities. Physical separability. Mixtures can often be separated by physical means, e.g., filtration, evaporation, distillation. Types of mixtures. Homogeneous mixtures solutions. Uniform throughout, with components indistinguishable to the naked eye. Solution. A specific type where a solute, e.g. salt, is completely dissolved in a solvent, e.g. water. Examples include salt water, air gaseous solution, and alloys solid solution. Water's polarity makes it an excellent universal solvent. Heterogeneous mixtures. Components remain separate and visibly distinct. Suspension. Particles are mixed into a fluid but not dissolved. They are large enough to scatter light and eventually settle out, e.g., muddy water, orange juice with pulp. They are often cloudy and chunky, colloid. Tiny particles are evenly distributed but not dissolved, small enough not to settle but large enough to scatter light, the Tyndall effect. Examples include milk, mayonnaise, and fog. Emulsions, e.g., salad dressing, are a type of colloid where immiscible liquids are dispersed with an emulsifier. Physical versus chemical changes. Physical change alters the arrangement of molecules but not their chemical structure, e.g., shredding cheese, boiling pasta, mixing ingredients. Often reversible. Chemical change involves the formation of new compounds and is generally irreversible, e.g., baking a cake. Separation techniques. The ability to separate mixtures based on physical properties is crucial for industry and science. Common methods include filtration, separating solids from liquids; evaporation, recovering a dissolved solid from a liquid; distillation, separating liquids with different boiling points; decanting, pouring off a liquid from a settled solid. Mixtures in nature and life. Blood, a complex suspension of cells, proteins, and nutrients. Soil, a heterogeneous mix of minerals, organic matter, water, and air. Seawater, a solution of salts, gases, and microscopic life. Clouds, colloids of water droplets in air. Mixtures demonstrate chemistries. Light touch, where substances can interact and coexist without permanent change, highlighting a balance between blending and distinctness. Chemical reactions are not just about what can happen, but how readily and under what conditions molecules react. For example, milk spoils quickly on a hot summer day but remains fresh longer in winter. The molecules themselves don't change, but the rate at which bacteria break them down increases dramatically with temperature. Temperature is a primary factor influencing reaction speed. Higher temperatures provide molecules with more energy, causing them to move faster, collide more frequently, and with greater force. Think of molecules as dancers. At low temperatures, they sway gently, occasionally bumping, but at high temperatures, they're breakdancing everywhere. More collisions increase the likelihood of bonds breaking and new ones forming, which is the essence of a chemical reaction. However, effective collisions require sufficient energy and proper orientation, much like a high five needing the right angle and timing. Heating a system ensures more collisions meet this energy requirement, overcoming the activation barrier, or energy hill molecules must climb. Concentration also significantly impacts reaction speed. A higher concentration of reactant particles in a given space leads to more frequent collisions. This is analogous to a crowded subway station, experiencing more accidental shoulder bumps than an empty one. Highly concentrated solutions react faster because there are more reactive particles interacting. Surface area plays a crucial role in reactions occurring at the surface of a substance, such as a solid reacting with a liquid or gas. Increasing the surface area accelerates these reactions. A sugar cube dissolves slowly, but powdered sugar dissolves almost instantly due to its increased surface area. Similarly, powdered substances, like spices or explosives, react more energetically because more particles are exposed, leading to more contact between reactants. While temperature, concentration, and surface area generally speed up reactions, some are inherently slow due to stable bonds, multiple steps, or complex rearrangements. In these cases, catalysts become essential. Catalysts provide an alternative, lower energy pathway for a reaction, acting as a shortcut. Enzymes are biological catalysts that enable vital reactions in the body to occur in seconds, rather than days or years, by positioning molecules and stabilizing transition states. Light can also influence reaction rates, with photons providing the energy to initiate certain reactions, as seen in photosynthesis and some photographic processes. Understanding reaction rates is vital in modern chemistry for designing industrial processes and medications. A reaction that is too slow may be impractical, while one that is too fast can be dangerous or produce unwanted byproducts. Chemists carefully adjust conditions, concentrations, solvents, and catalysts to achieve optimal reaction rates. Even in everyday life, reaction rates are at play. Browning meat, the Maillard reaction, relies on high temperatures. Too hot, and it burns. Too cool, and it stays bland. Refrigeration slows down spoilage by reducing the rates of chemical changes like fat oxidation and bacterial metabolism, preserving food, medicines, and even tissues for transplant. Some reactions are incredibly slow, appearing almost paused on human timescales, such as diamonds slowly turning into graphite or organic matter transforming into fossil fuel. Conversely, rapid, fleeting reactions, like the combustion of hydrogen and oxygen in a rocket engine, happen in an instant, releasing immense energy. These are critical in fields like explosives and propulsion. Ultimately, understanding reaction rates means grasping how molecules constantly move, collide, and decide to transform. This rate is influenced by external factors like heat, pressure, size, shape, concentration, and the presence of catalysts. Every bubbling pot, rusted hinge, and ripening peach is a molecular ballet, with some molecules racing towards change, others maintaining equilibrium, and many reacting at a pace synchronized with their environment. Chemistry, like life, often depends on the right timing, conditions, and a little patience for reactions to unfold perfectly. Chemistry isn't confined to labs or even Earth. It's the fundamental language of the universe. Across billions of years and unimaginable distances, atoms assemble, disassemble, and reconfigure. Gravity orchestrates their gathering, fusion transforms them within stars, and cold clouds preserve them. Occasionally, within this vastness, these very atoms gain consciousness, allowing us to gaze back at the stars and contemplate our origins. We are not separate from this cosmic narrative. We are an integral part of it. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stars, journeyed through space, and ultimately became woven into living beings. The same chemistry that constructed us also built galaxies, nebulae, and moons. We are collections of atoms that have learned to think, feel, and marvel at their own genesis. The cosmos isn't merely out there, it's also in here. Every time we look at the night sky, we witness a reflection of ourselves scattered among the stars. Whether it's hydrogen fusing in a distant sun, or a molecule forming on a dust grain in a frigid nebula, it is all chemistry. Quiet, elegant, and universally present. Even in moments of apparent stillness, chemistry is perpetually in motion. A cool cup of tea, a breath taken in the dark, the gentle creak of wood in a settling room. Beneath it all, atoms move, molecules shift, electrons dance, and forces balance. This rhythm is too subtle for us to see, and too constant for us to hear, yet it persists. Every moment, every object, every part of us is held together and transformed by the slow, steady, and sometimes spectacular poetry of chemistry. Throughout this exploration, we've journeyed through the diverse world of matter, from the smallest atoms to fiery stars, from rust on a garden gate to reactions within our cells. We've seen chemistry unfold rapidly, explosively, and brilliantly. However, we've also delved into its calm aspects. The patience of weathering stone, the dissolution of sugar, or the precise folding of proteins. Our journey began with atoms, the fundamental building blocks, each possessing a unique character with proton-filled centers and dynamic electron clouds, never truly at rest. We traced the unpredictable paths of electrons, discovering how their drifting, leaping, and orbital arrangements define all reactivity. We observed how bonds form, sometimes cooperatively, sometimes through theft, leading to the endless variety of chemical structures. We explored how energy fuels reactions, how heat and pressure can induce molecular collisions with the right force, and how sometimes a gentle nudge from a catalyst is all that's required. We encountered acids and bases, opposites in charge and personality, and learned how a simple pH change can dramatically alter reactivity. We examined the influence of temperature and pressure on particle interactions, speeding them up or holding them back. We explored equilibrium. where chemistry achieves a balanced stillness, not a cessation, but a harmonious hum of matched forward and reverse processes. Even explosions had their place, as rapid reactions released all their energy in brilliant, fleeting moments. We followed the dramatic story of carbon and the elegance of organic chemistry, revealing how this single element became the foundation for all living things. We traced electrons in redox reactions, constantly being passed, swapped or borrowed, and observed how batteries, metabolism and rust all share the same underlying principles. We met catalysts, the backstage crew of chemistry, witnessing how they gently guide reactions without being consumed. We unveiled the secrets of water, that peculiar and life-sustaining substance, whose hydrogen bonds and polarity make it the universal solvent for molecular life. Then we transitioned through states of matter, solids holding their form, liquids flowing, gases diffusing, and plasmas glowing, each revealing a distinct type of motion and freedom. We delved into mixtures, solutions, and suspensions, realizing that not everything reacts. Sometimes substances simply blend, swirl, or separate. In our study of reaction rates, we saw how time, heat, concentration, and shape all contribute to the speed at which chemical changes occur. From there, we ventured into the human body, exploring biochemistry, life's own subtle chemistry, and discovered how proteins, enzymes, DNA, and ATP form the intricate machinery of existence. Every heartbeat, every thought, every blink is powered by molecules, operating with a calm confidence that belies their complexity. Finally, we extended our exploration beyond ourselves to Earth's chemistry and the chemistry of the cosmos. Volcanoes, carbon cycles, planetary atmospheres, stardust, and interstellar clouds, all governed by the same fundamental rules and driven by the same forces of attraction, repulsion, energy, and transformation. Whether it's lightning in the sky or amino acids on a distant moon, chemistry connects everything. All of this reminds us that matter is never truly inert. It may appear motionless, resting in your palm as if doing nothing at all. But even then, it is reacting, changing, or preparing to do so. Particles are moving, bonds are vibrating, electrons are shifting. Even in a moment of silence, the universe hums with invisible activity. Stillness, it turns out, is teeming with life. There's something profoundly comforting in this realization. We inhabit a world that often prioritizes speed and spectacle. Yet, chemistry teaches us that slow, quiet change is equally powerful and often more enduring. Rocks weather, trees grow, cells divide, oceans absorb carbon. Reactions can blaze like fire or unfold over centuries. Some require energy, some release it, and some simply hover at the brink of balance. Behind every one of these reactions, no matter how fast, how small, or how seemingly ordinary, lies a story. A miniature narrative about atoms striving for stability, molecules seeking lower energy states, and systems finding their way to equilibrium. It's a chemistry not only of things but of desires, tendencies, and probabilities. The periodic table is more than just a list. It's a cast of characters, each element with its unique quirks, preferences, and bonding styles. Whether we consider how soap lifts grease, how batteries power flashlights, or how stars transform hydrogen into gold, we are witnessing chemistry in action. It is not separate from us, it is us. The chemistry of water is the chemistry of your blood. The chemistry of carbon is the chemistry of your thoughts. The chemistry of light is the chemistry of sight. As we conclude this journey through the chemistry of nearly everything, I hope you've experienced the wonder that lies beneath the surface of the everyday. I hope this has been interesting, but not so interesting that it disrupted your rest. If it did keep you awake, at least you've gained new insights about the world and perhaps about yourself before drifting off. If you're still peacefully listening with your eyes closed, I'd be delighted to know. Where in the world are you tuning in from? What time is it there? Are you nestled in bed under soft blankets or on the couch with a pet? Are you hearing the quiet of the night outside your window or the gentle hum of a distant city? Please share in the comments. I cherish hearing where this chemistry journey has taken you. If you found this exploration enjoyable, relaxing, interesting, or gently thought-provoking, please consider liking this video or subscribing to the channel. It helps me bring more such content to you and indicates that these gentle dives into science are adding a touch more wonder to the world. Thank you for being here and for joining me in this quiet celebration of how the universe operates, one invisible reaction at a time. And remember, even when nothing appears to be happening, chemistry is always at work. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, remains beautifully, endlessly alive.